Well, it brings me great pleasure once again to introduce our guests, Kyle Daruwalla and Ari Benjamin from Culture Arbor Lab. So, obviously, this is set 40, plus years ago. Do you recognize any connection between what they're doing and the work that you guys are doing, or has it just been left in the dust?
The day-to-day looks a little different. But yeah, algorithmically, I can detect similarities. Maybe, Kyle, do you want to weigh in on the AI side?
Yeah. Well, I think like an aspect they touched on a lot in the movie was the importance of the performance of the computers, how powerful they were, and then the technique they were using. You may have heard terms like search or tree or brute force, and basically throughout the history of chess playing, which is really, like Ari said, been a great lens into the development of artificial intelligence, it's been tightly linked to the development of computers. So for most of that period of time, and really up until the mid-2000s, the way chess playing agents work was exactly how they showed it in the movie. You'd basically have a way of specifying to the computer what the chessboard currently looks like, and the computer would have some way of saying, well, this is the next possible move I could make. If I made that move, what will my opponent make? And then back and forth, and it would really just search through all the possible moves, and most of the progress in AI for the longest time was driven really by computers getting faster. It's not that we got that much better at building AI, it's that computers got faster so we could just search more moves in a shorter amount of time. And I couldn't tell if the human actually lost at the end. I think he did, or maybe he just got frustrated by the other conference. Yeah, he's too human. But the first person to actually lose at chess to an agent was against Deep Blue, and that happened in 2000, I want to say.
Late 90s, I think.
Yeah, late 90s. Yeah, exactly.
Yeah.
And that agent was basically the same kind of programs you saw over here. The difference was it had access to lots of expertise knowledge about like the value of certain moves, and it was able to search through that knowledge really, really fast. And then the major advancement in AI between what they showed there and what happens today is neural networks, and that really drives what is in current artificial intelligence. And that was also driven by an advancement in computing. So the kinds of computers you saw in the movie and the kinds of computers we use for AI today are a little bit different. And we've developed a type of computer called a GPU. It's actually designed for like gaming, for showing things on your display really efficiently. But it turns out it was really, really good at running these neural network training programs where we could train these models based on data. And what that allowed AI agents to do is take something high, like exponentially complex, like the guy said in the movie, and turn it into a really compressed representation. So it could take the state of the board and maybe in a similar way a human might recognize that a whole bunch of different states are actually equivalent to each other, and that there's really one strategy I should be following in response to all of those states. And that was really the major difference between what we saw in the movie and then the AI agents that we see today. But the basic building block of trees and searching through moves is still there in current state-of-the-art AI.
So why is chess was such a great tool for teaching, getting computers to learn?
I think, because, well, keyword being learn, and because it is that state space, of 10 to the however many possible boards being so big means that you have to simplify the problem somehow. And I think that has the same character as many of the problems that we solve, that our nervous system solves, where if you actually tried to enumerate every single possible thing that you could do with your hands, with your muscles, or with the course of your day, I mean, it would be impossible. So you have to simplify somehow and develop some heuristics and rules about what you might evaluate, and these rely on well, you have to have some way to do that. And one, as Kyle was saying, a big change was to move from heuristics like a queen is worth 8 points and a pawn 5, and so on, to these neural networks that, inspired by how we think we also solve chess, would look at the state of the board and learn by adjusting all of the connections in these large neural networks to associate a state of the board with being overall better or worse. But if you were to ask a neural network, why exactly do you think that, you wouldn't quite get a clear answer. And such is the case for many people as well. It's very difficult for them to say.
So is there a way to explain to lay people what a neural network is? Or is it just too complicated?
It's not so bad. Yeah, I think the clearest way to think about it is really a shift in philosophy about how we think we work, but also what is the best route to develop artificially intelligent systems. And the shift, which Kyle was also mentioning, is somewhat a shift from having a symbolic state that represents things explicitly, and you have symbolic operations. And there's the broad shift that we've seen in AI is instead have neural networks where you have many different neurons or units and many different connections that connect them all, and you can make that connectionist system. You can make that series of edges and units to be any architecture you would like. It doesn't. What really matters is how you train that system, and when you train that system, it operates in such a way such that every connection in that system slightly changes, such that when information is propagating through that network, you get the right outcome at the end. And then if you made an error, then you go back through the system and say, okay, well, if this weight were slightly different, the error would have been a little lower. And then you just sort of do that over and over again without really understanding what any unit corresponds to or what any weight is doing until it gets better.
So it's learning.
It is learning. And as far as we have good theories about learning in the brain, the high-level principle of adjusting small connections is very similar.
So computers you're trying to get them to think more or to learn more like people learn, or is there a difference?
There are many differences and many similarities.
I know I'm asking you to take some complicated stuff, and we're asking kind of basic questions.
Well, let's see. I think
well, there's the one big similarity is that we kind of learn through examples, and in the case of the neural networks, like Ari was describing, they're also learning through examples by seeing data. They're getting a human actually collects the data and specifies when the neural network did the right thing and when it did the wrong thing. And so in that sense, it's learning in a similar way to us. But the actual mechanism, like the way the program knows how to change one of those connections based on getting it right or wrong, may or may not be exactly how the brain works. And one of the big differences between us and current AI systems is that usually you can learn very efficiently. You don't need to see an example of how to solve a problem many, many times before you can solve it correctly. But the current systems today usually need millions and millions of training examples, is what we call them, millions of opportunities to guess what's right and guess what's wrong and actually get a signal of how well it did.
Yeah. It's still, there's a lot of debate as to what the actual learning rules of the brain are. What are the algorithms, such that we could compare them to an AI system? So, we really don't quite know, but there's, I think like the history of chess and building chess is sort of a lens into this, but, and I think one of the themes of this movie was like, people struggling with their motivation as to why they're building AI systems. And I do think that a major motivation for many is to understand ourselves better. Of course, there are many, it'd be great to have great chess tutors for, children, but also by understanding, by trying for the first time to develop a system that we think works like us, we can begin to see what it really takes. Is it how we think it is, or is it actually a little harder to design like learning rules, learning algorithms that might be working in the brain? And one thing that motivates, I guess, a lot of the work at Cold Spring Harbor is to try to take is to try to take that starting point of developing AI systems and then bring that back to understanding how we think the brain might work.
I want to open it up. People have stuff. That didn't take long. You want to do it? We have some microphones we're going to roll around here. I know everyone feels like they speak really loudly and don't need a microphone, but take my word for it. The people in the back or the people in the front will be very appreciative.
Hi. So anyway, I had computer questions, but I had a movie observation. So they made a point of talking about the Turk, which was like a machine made in the 1700s, but actually behind the scenes, it was a human hidden in there playing. So it wasn't, any kind of automation. Now at the end of the movie, when the computer was playing the host of that whole conference, there was an acoustic coupler on the computer. I don't know if it's an old way of communications, hooked up to a phone. And it just hit me. I wonder if they were playing the same trick and there was someone behind the scenes actually feeding that computer's moves. So it wasn't the computer, it was just like the Turk, just 1980. So it was just an observation. I don't know if anyone else saw that.
Yeah, I wondered myself, and I don't know if any of you followed some of the controversy in the chess world from last year, but there were some murmurs that some chess champions were cheating by getting instructions, probably from a chess-playing AI agent, and that was helping these humans win their human tournament. So it's interesting how it's flipped.
There was someone there. Yeah. Okay. Yes. Two, let's go.
You have a couple of questions, but I'll start with one and maybe let me ask a second one. Is the underlying technology of the computer the same to run neural networks as to, run my desktop?
Yes, in some part, yes. The way the computer chip is built physically is, for the most part, largely the same. The main difference, like I was mentioning, is this thing called a GPU, a graphics processing unit. And so that type of computer is really, really good at doing the same thing, but many, many times and in parallel. So if you don't have to do like a complicated sequence of instructions, but you're kind of doing the same thing over and over again, but you just have to do it on, let's say, a lot of data at once, then that's what a GPU is really good at. You could think of like trying to draw, like what it was designed for is displaying stuff on your computer screen. So if you're like trying to draw everything on your screen, you have a 4K TV, every single little pixel in that TV, you kind of have to do the same thing over and over again to draw what should be in that pixel. And so that's what the GPU is really built for, but turns out it's really good at running the underlying program, the algorithm that's behind neural networks. And that's basically because, like Ari was describing, neural networks are just artificial neurons. You have the same neuron, it's just repeated over and over and over again, and it's just doing the same kind of computation over and over again for every single neuron, similar to like how every single pixel on your TV screen is a very similar computation. But yeah, like that's why as computers get better and faster and more energy efficient, we can go from neural networks that need like a very large server to run to something that can run on your phone. Like most of your phones are probably running neural networks on them right now.
One more then. I'm still not grasping the difference between brute force training and and training in this new neural sense. Seems to me, I think in my mind anyway, it's still, putting showing the computer lots and lots of data and having it, through practice and trial and error, figure out which is the best move in chess terminology. Could you clear up my not seeing the difference between those two things?
Yeah, so the thing we saw in the movie, which was the brute force aspect, in your computer program, you have some model of how a chess game should go. What are the possible moves when the board is in this state? What are the moves that are good? What are the moves that are bad? And you hard code those kinds of heuristics into the program. And then what the computer does is it just plays out the moves. It literally is just simulating the moves one after the other. And it's searching the future moves it could make and what the outcome might be. And then it's trying to pick the outcome that it thinks is the best. And that's how the brute force method works. So it's really about taking a model that you have of how a chess game should go, and just using that model to plan ahead and pick the best move by planning ahead as far as possible. Now, the difference between that and the neural network side is what the neural networks are really good at is taking data and coming up with a really efficient model. So let's say I'm a computer programmer and I want to write a chess program that's the best, then I need to put in all the different possible configurations the board might be in and all the possible moves I need to take in order for my program to actually plan ahead as best as possible. What a neural network lets me do is, instead of me having to write that into my program, the neural network can look at data, which is moves that humans have made, and actually learn which moves are the best. And then I don't personally have to come up with that list. It'll figure out what the best possible list is. And then there's still the brute force aspect. Once you have the neural network, it's your model of how a chess game should go, but you're still going to use that neural network model to still plan ahead. You just have a much better model than you did back in the 80s. Does that make sense?
Yeah, it does actually. Thank you.
In the last few years, we've been hearing a lot about quantum leaps being made in AI. We can see it a bit in the difference between Google and ChatGPT, but they say it's going to be geometrical and it's going to accelerate geometrically. Well, what are your feelings on that?
Like I was kind of alluding to at the start, a lot of the progress has been driven by computers actually getting faster. And so now we're kind of at a very interesting point where for a computer scientist, building a faster computer is a very hard thing to do. We've been kind of riding this wave, I guess, since we invented computers, where they kind of just got faster for free. Computer scientists really didn't have to put that much effort in for that exponential improvement in performance that you're talking about. But eventually that curve's got a plateau, and we're hitting that point now where getting that next 10x speed improvement from our computer is just not coming. And then at the same time, on the AI side of things, we've also been, thanks to the internet, getting access to lots and lots of data. But also we're hitting our limit there, where we don't have access to tons and tons of high quality data to train our models with. So both of these two things that are really the drivers of progress are saturating. And so, at least in my view, we're hitting a point where in order to take the next quantum leap, we need like a more creative solution to the actual problem, and we can't rely on these technologies just getting better as the main driver.
Yeah, I'm somewhat more mixed. I think like the neural networks that we have for the tasks that they're currently doing, such as language, the style of ChatGPT, the bigger they are, the better. So far, we haven't really seen the end of that, and people speculate that there is no end. The bigger you make these networks, the better they're going to be at those tasks, and that so many things fall out of being able to produce language. But what that means, though, I think what's really going to be the limit is money. To train a network at the size that large companies are training today costs hundreds of millions of dollars. 2 years ago, companies weren't putting that money in. It seemed like $1 million to press start seemed to be enough. But now there's enough money and interest that large companies are talking about the next scale. You know, like what does the $1 billion training run look like? And you know, what's the $10 billion? You soon start to get to the point where there's not really enough money even among the venture capitalists. And I think that will be somewhat of the major limiting factor.
There's a number of hands there, and there's someone up front.
Sure.
Hi, Kyle.
You'll be next, don't worry.
Yeah, just as far as like advancements in computation. So is the limiting factor more on the software side, or is it more on the hardware side?
Well, so I guess given the software that we have right now, I would say the limiting factor is more on the hardware side, alluding to like the money that Ari was talking about. The reason it costs so much more money to train a state-of-the-art AI agent is because it takes so much energy, and we can't get around the fact that energy is a finite resource on our planet, and to get the amount of energy it takes to run the computers and do the training that Ari's talking about costs a lot of money. So I guess like in my view, it's the hardware that's slowing down, and the only way, and when the hardware isn't improving, the only way is to just build more and more and more of it and pay more and more money to run larger and larger computers, because we want our models to be bigger and bigger and bigger. I think the innovation will come on the software side of things, where given a constrained amount of hardware, without spending more money, without building a bigger computer, how can we utilize it more efficiently?
There's a
I just had a question. I couldn't help notice the parallels in this movie between the humanness and between the mechanical, between the touchy-feely seminar that was going on about being born again and touching, and then we parallel how we're trying to teach the computer to play another computer, and then the parallel that it preferred to play a human, and the black and white of the checkerboard and the black and white of the pieces, and all of these contrasts going on. And as we look at AI today, I don't know if this is something you can comment on, but there's always the concern about, can we teach the computer to have the softer side of learning? You know, not that takes repeated experiences or algorithms or trials. Like even as a human, sometimes you just have one significant event. It's enough to teach you don't run in the road when there's a truck coming, you know. So I think that's one question. Can we teach it, and can we learn about our brain by learning how the computer learns about things like emotion, forgiveness, love, the softer stuff, not just how fast we can do something. Because sometimes the most significant things we've ever done are not things that we've done fast or learned fast. And the other piece is the scary part, like the how in 2001, and the computer talking back. And I know that I am not well versed in any of this. I don't even understand half of the technology you're talking about. But the fact that the computer and AI can, I'm not gonna say take over, but then maybe guide us in ways or influence us ways, and that may be based on the programmers, that may not be something we want as a society, as a population, a world, a path to go down. So I don't know if you can comment on any of that. I know it's a lot.
That was a lot. Okay. Well,
Yeah.
so jump in.
Definitely. Second question, great question. Let me talk about the first one first, though. Yeah, so the humanness of current AI systems is part of this. You're right, there's so much about the way we learn and interact and navigate through the world that is not present in AI systems. I think we're going to see, people are going to find amazing uses for what currently exists, the current style of AI systems, but we know, and there may be, no end to what engineers can achieve with that approach. But we know, or at least we as neuroscientists, know that there's enough about the brain that's not recognizable in those systems. People, yes, do theorize that there's a lot about our cognition that relates to predicting the future, and maybe a lot of intelligence is bootstrapped on that, and that may be fine, but there's a lot else, our emotional systems, our habitual systems, our surprise, and the way we model other minds and can interact with others, the way we have a continuing sense of self. None of these are present in AI systems, and I would wager won't be, because they're designed on only one out of the many principles that we know underlie the human mind. And I think it's important to remember, and it's also important, I think, to there's always danger, to your second question, in developing AI systems, but I would love to see them be developed in a way that is similar to our humanity rather than different and opaque, even for the same capability. But if we're going to trust and interact and really just understand our AI systems, they had better work something like us.
Yeah, just to add to that, in the movie, they had that one scene where the psychologist was talking to the AI system and asking questions about its soul and things like that, and then there was like the weird thing where the sonogram shows up and then the screen goes black. But actually there was one of the big news stories in AI, there was an engineer at Google talking to one of their early ChatGPT-like AI systems and believed that the AI system had been sentient, and he tried to blow the whistle on it. And eventually he was fired. But I think really what that speaks to is more about us. It's about our empathy. So it's not really necessarily that the AI systems have that softer side, but that we're looking at the words that are getting spit out of this machine and imparting onto it a very human aspect. And I think really a lot of what underlies some of that softer side is our ability to relate to each other.
There's someone up there who's been very patient. I keep telling him he's next.
Thank you. I'd like to go back to the neural network that you were talking about in the learning. So I think I understand there's a huge data set, and the connections get stronger and stronger, and it learns when it's more correct, and it learns from itself. What I don't understand are the hallucinations, when it out and out lies and AI comes up with literally a false citation. That's not coming from a data set now. So what's the latest thinking of when it hallucinates and literally gives something that's false and creates it out of nowhere?
Yeah, so that's a specific type of AI model, and the data that AI model is trained on is a language, so text mainly from the internet. And what it tries to do is you give it a word, and it tries to predict what is the next word in the sentence based on all the words that it's been given so far. And that's basically the task that it has to do. So when it's given something like coming up with a citation, right? You're asking it to write a legal document. It has to come up with a citation. For each word in that sentence, it tries to get those words as correct as possible. And for things like citations, the easiest way to do that is to get something that looks like a citation. It has the structure of a citation syntactically, but in terms of the overall logic of the paragraph that it's coming together with, it's not so important whether that was legally the right thing you should be citing in this brief. All that matters is that the words syntactically have the appearance of a citation, and it gets like a very good signal that it did the right thing. And so that's one reason, at least, why we get hallucinations with respect to citations.
Yeah, I think this is really great to like expand and think about, because I think it's fundamental to how these systems are trained and built that they will do this. Hallucination is the perfect word. I might also say dreaming or fantasizing. When you think about dreaming, you're in REM sleep, you're dreaming. Our nervous systems are trained, we think, to predict the future. So we know that balls fly through the air and people talk to us, and there's a natural course of things. But when I'm dreaming and it's untethered to a specific reality, those predictions feed on themselves and can start to generate things that are just of their own nature. And I would never say that my own dreams are relating to something that is actually the truth. Now, it could be related to the truth because I've been interacting with the real world during my waking hours, but that starts to prompt these self-generations. And that same thing is happening with these neural networks, and they're quite good at it, but it really is, they're continuing to dream as we interact with them.
Wow. There's some people up here, and we have time for a few more questions. There's someone here who's been very patient and working our way up. Steve, you want to go next?
So anyway, the never-ending advancement in computer technology and visual technology is key. We went from kilobytes to megabytes to microtechnology. Now we're dealing with nanotechnology on the level of atoms. The question is, eventually, we're going to run out. In other words, do we have to go to even a higher technology to be able, because there's so much data in AI, to be able to be effective, totally effective. Do we have the technology? No, we still have to go even further than that.
It's a good question. We haven't seen the end of the road yet, but yeah, these principles of memory, routing information, like the basic computer chip architecture that we have today, is it sufficient in principle to have something like a human-like intelligence? Is this somewhat the question? I would think yes, but I can only speculate. That's all I can say.
Yeah, I mean, I think in theory, yes. So, well, insofar as everything that humans do is just computing something, is similar to what a computer does, and we can find the right program for that, then in theory, yes. But the hard part is, of course, physically building a computer that realizes that theory. So, like, if I have a hypothetical computer in my brain that could do all of this, can I actually build a physical computer that has memory that large, that routes information back and forth efficiently enough that it isn't just going to get really, really hot, use up a lot of energy, and eventually just burn? That I'm less certain about. I mean, like you mentioned, computers are down to nanoscale now. There are new physical substrates like quantum computing that allow alternative means that don't have to deal, let's say, with as much of that physical limit, but they also have other challenges associated with them. And the kinds of problems that they might be well suited to solve, at least at this stage I don't know necessarily that there's a strong overlap with artificial intelligence. So it's unclear to me whether quantum computers or something like that would be the right solution to addressing it.
Over there, and then we'll come up here.
Yes, hi. So at the lab, maybe you can elaborate on what you actually do at the lab. You represent the neuroscience side and you represent the AI side. Do you collaborate together? Does one inform the other? If you could elaborate there, please.
Yeah. We collaborate a lot, the two of us, and also both of us collaborate with other neuroscientists and other AI scientists. AI as a general technology could be used for all sorts of things, and I think like the power to make it a force for good is to like apply it to key problems. And for me, that's like medicine and neuroscience. So one of the things I do is like a lot of like similar to ChatGPT understanding text on the internet. We can apply that to biological data. Very similar technologies applied to. I'm looking at like single cell. Record transcription. So mRNA, you can go into a large number of neurons in the brains of mice and see what genes is each of these transcribing. And the resulting data sets are extremely complicated. And we're hoping that similar AI-based technologies can help us understand that to some degree. And then we'll see if that circle can complete and help us to understand the brain in an algorithmic lens as well.
Yeah, I think I collaborate with Ari and a lot of other neuroscientists at the lab all the time. Part of what I do is listen to ideas that they have about how biology works and how the brain works and try to see if there's anything we can pull over to AI. A big part of my goal is to build AI systems that are more energy efficient to address some of the problems that we've been talking about. And a huge part of that is how to train it with less data. And the brain is a perfect model system for it, doing exactly that. So that's one part of what I do. The other part is applying the latest AI models we have to data that neuroscientists collect. So a lab that I work in, we study facial expressions in mice. So we have cameras, high resolution cameras. We record the mouse's face while it's doing a bunch of different things, and we try to understand the expressions that it's making. This can help us to better understand how expressions that we make reflect our own internal states and how that might change in the presence of disease or disorders.
All right, there's someone here. See you. Time for like one or two more questions. Yeah.
Okay, thank you both for coming. I have a chess question, and that is that recently, about a month ago, Elon Musk said that he predicted that chess would be essentially fully solved, like checkers, within 10 years. Is that merely a function of computing power? Is that what he's talking about?
So this was recently?
In May.
Isn't it already fully solved?
Yeah, like a good chunk of some of Elon Musk's claims. I don't fully understand where he's going, but yeah, I as far as I would know, chess is fully solved in the sense that we have AI agents that are capable of beating humans at chess, and we can also beat humans in games that are more complex than chess and have a bigger tree basically to search through.
Maybe he means like there's like such a concept as like game theoretic optimal, where and it does exist that there is a game theoretic optimal player for any deterministic game where it let's just say there's no randomness like chess, where no other game playing agent could ever beat it. So not even just better than any human, but like for checkers, this is the case. We know what game theoretic optimal playing looks like. Like tic-tac-toe, a lot of us learned this when we were young. The strategy is unbeatable. So there is an unbeatable strategy for chess, and maybe he thinks that that will be found in 10 years, and then after that, there's no more improvement. What do you think? Do you think in 10 years that would be achieved?
I mean, maybe. I'm not a game theory expert, but I'm not sure that the approach I would think would achieve that game theoretic optimal strategy would be training AI agents necessarily. In part because often we don't understand the strategies that the AI agent is actually taking and how it's making some of those decisions. So I'm not sure how we would show that it is the optimal strategy to take. But certainly, I guess, mathematicians could come up with that strategy. I don't know how they did it for checkers, so.
Yeah, maybe it would just be, can't train anything better than this one, so it's got to be the best.
Can't be that one.
Not sure.
All right, we have time for one more question.
Thank you. Thank you both. So I'm going to start with a very abstract question and maybe take it down and then you guys do whatever you can with it. So I think one of the problems that I've been interested in a long time is consciousness, right? Even today, the best models aren't conscious. I don't even think a model can train itself, right? It has to be told what was correct and incorrect somehow, I think. There's no initiative, right? It's not self-motivating. So my question is, in both of your disciplines, is there literature on that? Is there newer answers in the last 10 years as to whether that is even something that could be modeled or replicated? And I guess the less abstract question is, are models, does AI train itself today, or is it close to being able to be self-training at least?
I can go with the first question, maybe. And to say that there is literature on this in the last 10 years. Scientists are now able to get grant funding to study the problem of consciousness, which didn't so much used to be the case. And have they solved it? No. But there are theories that are being put forward. I think just last year there was a conference at NYU where a couple of the major theories that exist had a big debate on stage, and they had a reveal, or they had actually predicted a year before to do some fMRI experiments, and according to one theory they would observe one thing and a different theory the other, and they pulled the curtain and found that it wasn't very conclusive. They weren't quite sure. But it's definitely an open problem. I don't think I'm less optimistic that we have the conceptual tools to address that, and we would need in my opinion, a large revolution in our scientific thinking to be able to. But I'm happy that people are thinking about it.
Yeah, I mean, I guess going more on the second part of it, in some sense, AI agents can train themselves. A big part of how the current chess agents work is they actually play against themselves, and that helps them bootstrap. So it basically means that we don't have a lot of training data of actual human experts playing chess, but by the agent playing against itself, it can actually get a good chunk of the way there to a good performing agent, and then the data that we do have gets it the last mile to like a really good performing agent. And so that self-play is a very big part of how current AI agents work. But that's not quite exactly the same as what you're getting at, which is the motivation to actually engage with the world and learn from it. And it's true that AI agents don't have that, and I think a lot of philosophers who do talk about the extent to which AI mimics our intelligence and mimics consciousness, one of the major criticisms is that AI agents lack the desire to live, the desire to survive, and then also this idea of self-replication, right? We biological organisms reproduce and self-replicate, and that's a big part of what's missing from from AI. Whether that's an important part is a question of debate. Yeah, and I think another big aspect of the whole consciousness thing, as Ari alluded to, is that we lack the scientific vocabulary to really think formally about what consciousness actually is and what predictions we would have about the brain relating to it. But I think we can, get a good way there to understanding intelligence without ever understanding the nature of consciousness. Animals do very intelligent things, and plenty of people may not consider animals conscious to the same degree that we are, but that doesn't mean that they don't use the same strategies as we do to learn, and that we couldn't learn a lot about ourselves and our own intelligence from studying them. That's exactly what we do in neuroscience labs, is study animals.
Is part of the challenge is that we don't fully understand why we're conscious. I mean, why this big computer in our skull has all these interesting emotions and stuff. And
Yeah, I mean, we have no idea is the problem, and our language for describing, our formal languages are those of information and computation. There's no place for subjectivity or subjective phenomena within those notions. And in my day to day and Kyle's day to day, we're working within the context of information and computation, and it does not seem to me that we could fully explain all behavior of any animal or AI system on that plane, and never arise to subjectivity.
Yeah, I mean, there are some theories that have tried to use the language that we do have, like information, to describe consciousness, and under those theories, a light bulb is partially conscious. So, it really points to, I think, the lack of the ability for formal or mathematical tools to describe this phenomenon that we all kind of experience. I guess one last hot take from my perspective is that I think of consciousness as something like thinking that the Earth is at the center of the universe. It's like a human-centric bias that we have for how intelligence should be, but may not be the reality of what's really going on in these systems. And yeah.
I actually asked ChatGPT the question about, is the glass half empty or is the glass half full? And it carved out and defended a position, which that was my test. Like, is this really different, And to me, it was very convincing. But I know, I have a computer background, I know it's still generative, not creative, but still very convincing.
well, it's pretty complicated. So we're out of time now, but we want to thank our guests for coming here. Thank all of you for coming and being part of this. Thank you all.